Google looks to finally be utilizing the data that they have, and they created a text-to-video model here called Lumiere. I think that's how you pronounce it. And YouTube has, or Google has all of YouTube, and they definitely have the compute to do something like this. So if anyone should be able to create a good text-to-video model, it should be Google. I would show you the demo on my tablet. However, it like crashes every time I do it. So they have a demo here. The videos look quite good compared to a lot of other text-to-video models, and they utilize a lot of similar methods as old text-to-video models, or as other text-to-video models. The important part about it is probably the data that they have. Not everyone has all of YouTube. So I'm guessing that the quality comes from the data that they have rather than the model specifically. Though it's still good to kind of look at the model because they make some important changes to current models that may actually make it better. Who knows if it's the architecture or the data or both? It's probably the data though. Well, it's probably a mix of the two. Yeah, so diffusion models to begin with. So you start off with an image for your diffusion model, and we'll call this x0. So gotta draw the good old picture of a cat. There we go, if you can call that a cat. Then what you do is you define a function. It's usually called p, and what p does is it adds a little bit of noise to your image. So we go one step into the process, and there's a little bit more noise in the image, or rather there was no noise and now there's some. You then take a second step and you add a little bit more noise to the image. So p, this would be x1, t is equal to 0, t is equal to 1, and this would be x2, t is equal to 2, and at x2 you add a little bit more noise to the image, so it looks something like this, perhaps, and then you keep on doing this over and over again, and you end up in a final state, which is pure Gaussian noise. So this here is just Gaussian noise. And this is xt, and this is t is equal to big T, which is equal to usually 1,000. This is the DDPM procedure, essentially the discretized form. So you can define this, and I'm going to define it in a not so mathematically sound way, but one that's more intuitive and one that directly, like it pretty much directly translates over to DDPM. It's almost the same formula. So we have 1 minus alpha t times x0 plus alpha t epsilon, where alpha 0, so alpha at time step 0, is going to be equal to 0, and alpha sub big T is equal to 1. So, and epsilon is sampled from a standard normal. There we go. So that's all that's happening here. It's just an interpolation to get to any image in this chain. And it's actually not a chain, it's actually a continuum, but it's a lot easier to like visualize it as a chain. So this here defines the interpolation, and at time step 0, we have 100% of our signal, so 1 minus 0, 100% of our signal, and 0 times the noise. And when it is big T, at the last step in the diffusion process, we have 100%, we have no signal and 100% noise, and anywhere in between is just an interpolation of the two. So that's the forward process in a diffusion model. Let me move this down. Now the reverse process is going to be learned by our model. So we're going to call this m theta. And m theta is just going to take the current step and it's going to reverse it once, m theta. Rather, it's actually going to take whatever the current step is and predict all the noise in the image, and you'll get the previous image from that. So if I take this image here, there, and I throw this through our model, m theta, then we would get out the same, or we would get out all the noise in the image, theoretically. So this would give us all this noise here, like that. So that's all the model's doing. And you can just subtract the noise from the image, and that gives you your image here. And yeah, all you do is you train the model at any step in this procedure uniformly. So you basically sample a random, I guess, a random value of alpha. So alpha would be sampled from a uniform distribution on 0 and t, so basically anywhere in the chain. And then you sample some noise from standard normal, and you just step somewhere in this, you step into the chain. So maybe you step in this part right here, somewhere in the chain, and all you do is you have the model predict the noise at that part. I don't know why I'm erasing that. The loss function probably makes it more intuitive. So if I sum over all the pixels, so whatever, sum over all the pixels in the image, I guess I and x, and the this would be epsilon minus, it would be m theta of xt. And if I rewrite it out like this, I and x, epsilon, I guess you need indexing, it's fine. I won't worry about the indexing, minus m theta of, and xt is just our interpolation up here. So this will be 1 minus alpha t, and it would be x0 plus alpha t epsilon, and I guess it would be epsilon t, like that. So, and that would be epsilon t. So all you're doing is you take an image, x0, you add some noise to the image, and it gives you this noisy image here, xt. And you feed that through the model, and all the model learns to do is remove the signal, so remove the image part from the noisy image, and it gives you the noise, and you can directly remove that via reversing this formula to get it, or to get the image you're looking for. To get the original image, we can just take this here. So it would be xt is equal to 1 minus alpha t x0 plus alpha t epsilon, and we can just solve for x0. So x0 is equal to, that would be, oh, that's xt minus alpha t epsilon over 1 minus alpha t. So you can basically go to x0, assuming your model's perfect, but since it's not, you basically solve this like an ODE, because the trajectories aren't going to be perfect. So you do something like this, xt minus that. So you basically have your current image here, and this is kind of the step, and then you multiply by some variance factor. And this is kind of a step in the direction of x0, and that would be xt minus 1, of x0. So this is the direction of x0, and you're basically stepping in that direction to move xt closer to x0. So the way I like to kind of look at this is, if I have some trajectory here, and this is x0, and this is xt, well, I'm going to make this xt here. So this is basically our noise. Then what the model can do is it takes the input at some intermediate step here. It'll predict a trajectory, and what you do is you step in that trajectory a little bit here, instead of going all the way over here, because that's not going to give you the image that you want, because the trajectory is going to be a disgusting mess that we don't understand. So that's all you're doing to sample. Given any xt, you can get x0 if you do enough steps, and that's how the solvers work. Yeah, this is just kind of a visualization I like to have, basically going from xt to x0. To do a complete sampling, what you do is you take xt and you initialize it. So basically you start at this part of the chain, and you do that by saying we're going to initialize xt to be pure Gaussian noise. So our image is just 100% Gaussian noise. And what we're going to do is we're going to take one step at a time along this chain to give us the original image, essentially stepping one step at a time along this trajectory here in the ODE that you're solving. So we would get x sub big T minus 1 if we pass this through the model. so m theta of xt. We would rather get the noise, so we'll say f that. So we basically do a step in the direction of that this says to go to. So this basically gives you the direction of x0, and you step in that direction, and that gives you one step closer to the image that you're going to get. And then you do x sub t minus 2 is equal to f of m theta of x sub t minus 1. So just plugging that in, and you repeat this process over and over again. So you're basically iteratively refining this noise here into the image that you want. So that's diffusion. Now what is m theta? So m theta is, let me get this image over here. There we go. So we have our image here. This is x, and x is going to be an r of L by W by 3, or 3 by L by W, depending on how you want to order it, where W is the number of channels, so RGB. And what you'll do is send this through a convolution layer. So this will just be sent through a convolution layer, and it'll blow up the channels to D, and then you send it through a downsampling layer. So I guess this would blow it up to D channels instead. Then you send it through another convolution, and then you send it through a downsampler. So this just upscales the channels. And the downsampler is just like, initially you can think it was initially like an average pooling, some pooling operation. Now this is a learned kernel here. If you've seen convolutional neural networks before, you've seen a downsampler. It was in the good old, it was in all the original convolutional neural networks. They're used there because you need to downsample your data to basically extract the important features and to make it more computationally sound, because you can't have infinite convolutions to get your output. So basically to compress the input a little bit. So you have your downsampler, and the downsampler basically gives you an image, or rather your compressed features here. And if this is L by W, then this would be L over 2 by W over 2. But also it has D 2 times D channels, or something similar to that. You increase the number of channels as well. You then send this through another convolution block, and then another downsampler block. And you get out another set of images or features, like so, which is L over 4 by W over 4. And then you would have 2D features, or 4D features, something like that. So you upscale the number of features again. You then have a middle block. The middle block is usually composed of an attention mechanism, a convolution, and then another attention mechanism. And to do the attention mechanism, you can think of, if I have an image like this, so it's a volumetric data where it's L by W by D, I can essentially tokenize it by taking each part of the image and flattening it. So this first part here would become the first token. That's just pixel 1 all over, where this is D-dimensional. And then I take this segment over here. So W would be, like the W index would be 2, and the length index would be 1 still. And this would give you another vector here. And then you just stack this over and over again for all the vectors in here. You throw this through your attention, did not mean to do that. You throw this through your attention module, and you get out your set of features here. And essentially this gives you a global routing, because this pixel over here can send information to this pixel over here, and this pixel over here can send information to this pixel over here. So it's a global routing. And that's why you usually have the attention over here. And since attention is so expensive, it's nice to have it in the middle block. So the middle block is usually like an attention, and then a convolution, and then another attention, something like that. And then you just do your upscaling. So you would upscale, and this would just be an inverted convolution. And this would give you your image, which is L over 2, W over 2 by D, or 2D, so whatever you had over here. You pass this through another convolution, and then you pass this through another upsampler. And you get out your big image here, so L by W by D. and you pass this through another convolution, maybe some set of convolutions, and you get out your output. And your output will be this image here, and hopefully it'll be the image with all the signal removed, so just the noise. And this is your model. And you just train this using this objective over here. So that's it. And it's just a normal UNet with attention in it. And if you're curious to add text conditioning, all you do is you add a attention module like here. You add it all over the network, and the text is just used as cross conditioning. So you have your text here, and you just use it to cross condition. If you're curious, I'm not going to go into it here, how to condition it and all that, and not how to make this a latent a diffusion model, but you can do that with like stable diffusion. And the stable diffusion paper tells you how you make this more efficient and how you add text conditioning and stuff like that. But it's just add-ons. So this is pixel diffusion. Stable diffusion is latent diffusion. Google, in this case, uses pixel diffusion. Anyways, that is normal diffusion. So how do we turn this into a video? We can take our chain here, and we can just duplicate it. So we have our chain here. And what if we just add a chain in parallel with it? That is not working well right here. So this chain here, let's call it, I've already used T, so I'll call this S0, and this will be S1. So this will basically be our first, I'll call it F. F is equal to 0, so this will be our first frame in the video, and this will be the second frame in the video. And the idea is to generate your frames in parallel together. So I guess in this case, like the function, like the model basically takes this pair of images in, and it produces the next pair. It produces the denoising step for that pair of images. So I guess it'd be easier to examine it like this. If I have a set of images here, and these will be our noisy images at xt. And this, so that'll be S, and this will be, so that'll be our sequence length, or rather the number of frames. So I'll do number of frames. And all of these will be L by W and they also have D dimensions. So this will be RGB to start out with. And this will just be our XT. So XT, you send this, so our noisy images, you send this through our model M theta, which will expand to be 3-dimensional. Right now, it'll only process spatially, but we also want it to process temporally. So you send this through the model, and the model will output the images here, and hopefully it'll output the noise to generate a video so that these frames are kind of sequentially ordered. So this frame would know about this frame, would know about this frame, would know about this frame. And instead of generating it image by image, you throw this through the model in parallel, and you add a few modules, and it should have temporal consistency along this. Otherwise, it would just generate 4 images that are pretty random. So we want temporal consistency within our model, and hopefully this will predict the noise in these images that defines a video with temporal consistency. At least that's the hope, and that's what they design M theta to do. So it's basically you have multiple trajectories that the model is predicting in parallel, and you can think of that trajectory as just the video itself. So it's multiple, rather than it being just an image, you can think of it as being this volumetric space that it's working with, as opposed to just this image here. So how do they do that? They basically define 2 parts. So they say they first train a UNet, and then they train this super resolution for, I think it's spatial super resolution. So this part here isn't that important. It's just a upscaler. This part here is pretty important though, and that's basically the main part that they're working with. So, or that they're changing. So they take the unit and they take a pre-trained unit. So assuming we already have a unit that's been trained on images, which is quite easy to find now. There's units everywhere, or there's diffusion models everywhere that have already been trained. So it's quite easy to find a diffusion model that already works with images, and they want to adapt it to work with videos. That's a lot easier than just going straight to videos. So they define three parts. They define spatial resizing, they define spatial temporal resizing, and then they do conv-based inflation and attention-based inflation. So there's three parts to it. Now, spatial temporal sampling or resizing is pretty simple, but basically, instead of just sampling the images using this downsampling operator, where you downsample the image itself. So you would have some kernel here, and it just downsamples the image spatially. So it would go from h to h over 2. You also want to downsample it temporally, so you want to go from t to t over 2. And doing it in this way actually gives some nice properties with the convolution-based inflation that we'll see in a sec. So essentially, if you have a set of images here, so your video, your frames, one more, you can easily just downsample them spatially. So that's just nearest neighbors downsampling, or through a kernel, a convolution. A better way, or what you also want to add, is the temporal downsampling. So we would want to downsample this to 3 frames that are smaller. I guess I could draw them like that, really small frames. And if you just do something like nearest neighbors, you could do something like this, where I take the first 2 frames, and then that becomes the first frame. And I can just do something like average the two together. And then I take the next 2 frames, and then that's the second frame. And then I take the last 2 frames, and that's the third frame. And then I downsample spatially as well for each of those. There's other ways of doing it, obviously, and that's obviously not the way they end up doing it. They use a 3D convolution to basically downsample temporally, spatially, and spatially. And it's no different than just a normal convolution that downsamples spatially. You just have the extra temporal axis. And this is nice because this first image here, this frame, does not represent 1 frame. It represents 2 frames. And you can think, if you use if you think about using a smarter way, perhaps we make these first 3 images be the first frame, and the next 3 be the second frame, and so on. Then this first frame will hold more information, more frame information, rather than just being the 1 frame itself. So this is nice properties with the convolution operator. So all you're doing is, instead of downsampling spatially, you do spatially and temporally. And they note that for some reason this hasn't been done before, where other papers haven't done spatial temporal downsampling. Really, there haven't been a lot of them. And then you do the same with upscaling. So you upscale spatially, and you upscale temporally, like so. Now, the 2 operations they add, because we want to adapt this unit, is a convolution and attention based inflation. So if we look at our unit here, what we can do is we can add a convolution, say right here, and right here, and right here, and right here. So basically, after every convolution we had before, we can add our own convolution, and this convolution is going to be a spatial, or it's not going to be it's going to be a temporal convolution, in a way. So this is basically going to just be a 2D convolution. So you have your spatial layers, and you keep your old spatial layers frozen. So the C we had here, we keep that C frozen, and we add the new C in. So a new convolution on top of our unit, and we keep the old parameters frozen, because we want it to retain the knowledge it had previously, and it's also expensive to train those layers as well. So all they have is a 2D convolution, and this is a spatial convolution. However, remember that this feature here does not just represent one. It doesn't just represent one frame. It represents multiple frames. So doing a spatial convolution on this frame is essentially doing a convolution on multiple frames. So a 2D convolution with temporal downsampling gives you the very nice property that it will manipulate multiple frames. It'll work with multiple frames implicitly, rather than it only working with a single frame if you don't do temporal downsampling. And that means you don't have to do a 3D convolution for every convolution operator here. You only have to do the 3D convolution for up and downsampling. So then they have norm and activation, normal, ResNet stuff, and then they have more norms, a convolution, and a linear projection, just basically transforming the features. So this here basically defines a local temporal convolution because of this 2D convolution here. So you can think of if you can think of a convolution on this frame here being a convolution on, I defined it as 2, so these 2 frames here. And that defines that locality there. So that's nice, but we can also add a global operator, which is attention. So we have, they specifically mention that the attention blocks go in the bottom layer because attention is so expensive. So that's what we have down here. You add the attention blocks, say here, the new attention blocks, after the old blocks. And all the new attention blocks do is, instead of taking an image like this, so this is our image, L by W by D, and basically taking each feature and throwing it through the attention module, you do that with a video now. So with the video, you would have this volumetric space here, and that would represent frame 1. And then you have a second volumetric space here, and that would represent frame 2. So that would be F2, LWD. And you do this for all your frames. So you have a volumetric space for all your frames, and that would be D. And essentially all you do is you take the features like we did before, and this would give you your set of features ordered by the index you define it by. So that would be D. And each of these would represent a pixel in this volumetric space here. And this would represent this image here, just flattened out. But you do the same for all the images or all frames in the video. So this one would go here, and so on. And you do this for these frames here, like that. And that would be transformed into that. And then you just do attention on these here, like that. And then it'll output your pixels again, and you can just reshape them back into your video that you had here. I drew it out over here as well. And essentially what this does is it says if I have a pixel here, it can attend to every other pixel in the video at any time. So it could attend to this first pixel here in this first frame, or the pixels can attend to themselves, or can attend to pixels within the same image as well. And I'm guessing they add positional encoding to this to ensure that it knows where, like what the frame ordering is. But that's essentially that essentially allows you to get a global context, sending information globally around the video, which is very important so that you can get a global consistency on the video itself. So they add these 3 things. They add the resizing, they add the inflation, the conv inflation, the locality, and the attention-based inflation with which gives you your global part. So you freeze the old unit, you add these new layers on, and then you train it. Instead of training it where this is the input image and this is the output image, you train it where this is the input video and this is the output video. And rather, the unit wouldn't output the video, it would output the noise, like we showed before. So that's all. And you train it the exact same way, except you train it in a similar way, which we'll get into in a sec. But you can think of it as training it in the exact same way, where the output is just the MSE between this, the prediction, and the noise that was added to these images here. So normal, diffusion. So that's this unit here. And then what they do is they define this SR thing, which basically is just a super resolution. So yeah, that's I mean, that's just a super resolution. So probably like some auto encoder or something like that, or maybe some inverter, or maybe some GAN that increases the resolution. You can define, or you can find those out. You can they I don't know if they train their own or not, but you can find those just out on the internet. Just a super resolution, spatial super resolution. They don't do temporal super resolution because the temporal part is the same before the unit and after the unit. It's just within the unit that it changes. So yeah, that's the unit. Now, how do you, there's a special thing that I want to mention for training this. So they mention it down here, multi-diffusion. So instead of just, instead of giving the model the entire video, which is computationally challenging, you instead break up your video. So if you have, say, we'll define 6 frames here, 5, 6, you can separate these two, and you separate them with an overlap. So let's say we have the first 4 frames go into batch 1, so 1, 2, 3, and 4. And then you have the next 4, or then you have these frames go here. So it'd be the last one, this one, but these 2 frames are shared between the batches, and this defines an overlap. And the overlap is so you can combine the videos smoothly. So you then send these through the model. So each of these would go through the model m theta, like that. And it'll output a set of frames, which is the noise that it wants to remove, like so. And what you do is you basically, if I go back over here, you have this overlap, and you basically need to combine these two. So you do that by just taking this frame, and then you have this frame here, which is going to be a combination of these two. And you have a frame right here, which is a combination of these two. And you have these 2 frames over here. So the way you combine them is using something called multi-diffusion, and it's essentially just a smooth way of combining these two. I don't think it's that important, but it's just a smooth way to combine the frames. And then you send this through your super resolution. You send it through super resolution, and then it upscales each of these images here. So you would have a larger resolution, but same temporal size. And yeah, so that's how they train it. Or rather, that's not how they train it. That's how they. That's just whenever you're doing inference, you have to send it piece by piece. And this, once it's trained, you basically have this overlap here, and the overlap allows you to continue the video. It allows you to continue the video and keep this consistency here without having too much computation cost. So that's just a side note that they kind of had. One last thing that they do is they train the model using conditional generation, and to do that, you don't just send in the images. So you have your images here, like so. So these would be your images X, and these would be in R L by W by 3. But you also they fine tune it with a mask. So once this thing is trained, they also want to do in-painting and some cool stuff with masking. So you define or rather conditioning and then masking. And that allows you to condition it on like a video and then change the style of the video. Or it also allows you to just do that for a certain part of the video using the mask. So it would be 1 where you don't want to change it, and 0 where you do. So you can define that however you want. So that would be L by W, and this would be L by W by 3. I guess that'll be 1. And you just stack these, and you basically get your features. We'll call this X hat. which is a set of images, which and you just stack these along the channel axis. So it would be R by L by W by 7. And you send this through the model, and then you train it in such a way that it learns how to do this masking. They talk about it over here. So you get out you get your 7 inputs and yeah, your time. And they say, yeah, they expand the channel dimension because they're fine-tuning this from 3 to 7 in order to accommodate the shape and fine-tune the base text-to-video model to denoise J based off the conditioning and the mask. So you can do this in a few ways. There may be a few things you want to do, like in-painting. In-painting would be nice to do. So all you do is you give it a mask where you want to paint it, and then it diffuses that part of the mask, and it learns to copy. Basically, it learns to copy where the mask is 1, and it learns to change wherever the mask is 0. So that's in-painting conditioning, and yeah, they have that here. So you can basically in-paint the video and say, I only give it a video. So give it a video of like a butterfly flapping its wings, and you say, I only want to change this part of the video. So then you change the style of that part of the video. Another thing they do is if you only have an image of a butterfly with wings and you only want to add video to that part, you can just give it the image and mask out that part using the mask style over here. And then it'll only generate video for that one part in the image. You can copy the image to all the frames and then mask out that part there. So yeah, just an add-on that they kind of add to allow you to do cool things like cinema graphics and in-painting. Other than that, they have some results. I do not it looks pretty good if you go look at the demos and stuff. I mean, the benchmark says they beat everyone. This is not an open source model, so there's no way to kind of confirm that. But the demo that they have looks good. I don't know if we'll ever see this model. Hopefully, someone can reproduce it. But yeah, that's Lumiere, the Google's text-to-video model. Very interesting model, and yeah, hopefully we'll be able to use it.